Okay. Hello, everyone. Good morning, ladies and gentlemen. I'm Rifkat Yarma from ICWT Technology Bandung, Indonesia. Today, I'm here to be your presenter of the paper titled EVA in Name Data Networking NDN Case Study on Inherent Topology. Without much talk, let's just see through the paper together. NDN, Name Data Networking. I'm sure this term is not a rare thing anymore, especially for the network enthusiasts. NDN is a new purpose network architecture that hopefully will be applied soon in return to the IP network or just get along applied with it. NDN is a promising information-centric ICN architecture that it means that NDN will near the content to the user done by caching on NDN routers. The working process will be like this. NDN will do the routing and forwarding by requesting the data to the network, and the reply will come from the producer from the server instead from the nearest node. I mean from the nearest node instead of the origin server or origin server. There are terms that will be used commonly throughout the experiment, which are the interest packet as a user request packet and also the data packets as a producer's reply packet. With these advancements of IP network, NDN is expected to significantly improve network application efficiency. However, the bad news is because of its efficient implementation, NDN is currently under threat by cyber attacks. The common one done in NDN is the DOS, starting with EVA. Interest loading attack, EVA, uses several actors to send malicious interest packets by requesting either existing or non-existing content in order to overload the legitimate producer. So therefore, the legitimate producer couldn't reply all the request packets from the consumer, from the user. Here we have picture that represent the scenario of EVA attack. There are more than one attackers that will send huge interest packet to the legitimate producer in order to overload it. And yeah, that's the scenario. Next, let's jump to the simulation. We've done simulation, starting by designing the inherent topology in a text file, and then next we go to the we go designing an EVA scenario utilizing mini NDN emulator, and we use inherent topology. Indonesia Higher Education Network is a communication network technologies and information technologies that connects all universities in Indonesia. The network, on a side note, the network was built by the Directorate General of Higher Education in 2006. In this simulation, we want to compare producer who work normally with producer who have had an EVA attack in order to determine how well the producer performs in meeting consumer demand after experiencing the attack that will be run. And we've summarized the simulation in the symbol table containing several parameters, the S size, the ID size, and so on, followed by its value. The main idea of the simulation, we want to send interest packets from attackers utilizing several delivery efforts with various interest counts and various time delay to the legitimate producer. After the result we got, then we will do analysis on consumer satisfaction. Consumer satisfaction is a fraction of interest packet and data packet. And as stated before, we conduct the experiment using several delivery efforts, several approaches, and those will be like this. First, we have two conditions. The consumer will be located near the producer, and the consumer will be located farther from the producer. And furthermore, for each every position of consumer, we will conduct the attack before and after consumer's interest packet sent. So in total, we have four conditions here, four cases to be analyzed later. As stated in the table, we use one producer, one consumer, attackers, two attackers, For the producer, we use sabang note. Consumers, we use lampung note. The case of consumer might consult to the producer. Jogja note, the case of consumer made further from the producers. And attackers, we use Natuna and Tual notes. Result. We've analyzed for those for cases, for conditions as stated in the previous chapter for the first starting with first section, interest packets sent before attack. First cases. First case. The consumer's position made closer to the producer. We've summarized the result in the table and also graph. In the table, we can see we use several parameters, interest attack, 1000 to 2000, time delay, zero point 0.5 to 2.5. And our focus here to analyze the satisfaction we got. The graph is made by the result written in the table. Starting from 1000 attackers interest for 500 milliseconds, it has low satisfaction. As we can see here in the table, interest we got 78 and satisfaction we got only 70. It has low satisfaction. We could say that this is as a result of the producer being overloaded with requests, which will rise the packet delay. As time raised, the satisfaction is increased nearly to the number of interests sent. We could say that the longer time there is for the interest to travel, the more time there is for the attacker's interest to be dealt with. As the number of attackers' interests increase, the number of interest attack increase, the degree of satisfaction decreases even more, as expected here. And with the same reason, same cause that this can occur happens with happens because of the producer receiving a rising number of interests, which then will allow the producer to process those interests more slowly. Second case, the consumer positions made farther from the producer. We also have the table here and also the graph as well. And in this case, we want to test whether the latency is raised or not to represent the farther position of consumer. Again, starting with 1000 attackers interest, the interest attack uh, the interest attack we can see in the table that doesn't interfere the satisfaction we got. Interest we got all in hundreds, and satisfaction we got as well. We got all in hundreds as well. It means that this interest attack doesn't really interfere the satisfaction we got. Unfortunately, for 1000 interest attack, we see a little bit an inconsistency here in the satisfaction. With interest all in hundreds, satisfaction we got is up and down here in the table. But the good thing is that the satisfaction is going up to 1000. Since we find that an inconsistency, we just directly analyze the higher interest attack 2000, and we can see that it seems like our theorem is correct all along. The longer the time, the higher the satisfaction can still be got up to the same number of interests. That's the result. That's the cause. Next session, interest packets sent after attack. The third case, the consumer is made closer to the producer. The result here is pretty similar for with the first case. The satisfaction get has slightly lower than the first case. That this shows the difference between the attack run before and after doesn't really that matter. However, this this cases this case, the interest attack sent before the consumer requesting still has impacted the satisfaction more compared to the interest attack sent after the consumer requesting. It is stated in the case is the compare the compared case is located in the first case, and this because of this case, in this case, the producer will process some attacker's interest first, as the attacker's interest arrives earlier compared to the legitimate interest. As uh, as we use in logic, we use our logic that the packet that will be processed first is the packet will that arrive earlier than the other packets. Last case, the consumer's position made farther from the producer. As expected, 1,000 interest attack doesn't really affect the satisfaction. So we just immediately jump to the higher interest attack. And the result shows that the satisfaction got is slightly lower than the second case. Based on the experiments conducted, we could make we could make an equation that of satisfaction after meeting interest attack. Here, T divided by IA time divided by interest attack is proportional to the out satisfaction. Out satisfaction value will be will have will the OS value will be lower or maybe equal than out interest. OS will be lower or equal than OI. So this OS this out satisfaction will not have value that will be higher than the OI, the out interest. That's the result. The experiment is really fascinating, isn't it? Okay, we finally reached the conclusion. 5 points here. First, EVA attacks can attack consumer satisfaction due to increased latency. The longer the time there is for the interest to travel, the more time there is for the attacker's interest to be dealt with. The more attacker's interest sent to the producer, the more effective the attack will be. Legitimate interest packets sent after attack has got impacted the consumer satisfaction more. The maximum out satisfaction value is the same as out interest, which means all interest packets sent by the consumer got replied from the producer in the form of data packets. For the future work, we hope that will be carried out to explore interest loading attacks with more complex schemes or even more advanced in type of interest type like, for example, TIVA, collusive interest loading attack, ETIVA, improved collusive interest loading attack, and so on. That's all. Thank you. Really appreciate your attention. Maybe we still have a few minutes for anyone want to ask a question with pleasure. Please.